Okay, this video is going to walk us through how the acceleration due to gravity is calculated on a planetary scale. So far, we've just been on Earth. We've said gravity is 9.8 meters per second squared, which is true anywhere in the general vicinity of the surface of the Earth. The Earth's surface, whether you're a mile high up here in Colorado or down at sea level or way up at the top of Everest, none of those places are really significantly different enough to really vary from 9.8. Up at top of Everest, maybe you're down in like a little bit less. I really don't know. I haven't done the calculations. That would be a fun side um, calculation to do, is find out, what is the acceleration of gravity at Everest. And um, actually, after doing today's lesson, you'll have the ability to figure that out. But anyway, we're looking more at like a planetary scale. After doing today's lesson, you'll see on a small scale, like you sitting next to your objects on the desk, there's not much gravity going on there, which you know. Objects on your desk aren't just flying at you. So, pretty clearly, gravity is a weaker force. You need a very, very, very large object like planets, stars. That's pretty much it. Planets, stars, black holes, things like that. Um, that's pretty much it in terms of things large with enough gravity. The Death Star. That's things with enough gravity to actually be noticeable. Your gravity not noticeable. Gravity is a reasonably weak force unless you have a lot of mass. However, it's one of the dominant forces of the universe because there's some big things out there with a lot of gravity. So we're going to look at that in these notes. So this is just a recap of those goals I just went over. We're going to look at gravity. We're going to look at what kind of factors go into gravity. We're going to do some gravity calculations. We're going to look at our first constant in physics. Physics has a lot of constants. Science in general has a lot of constants that convert units from one to another. We're going to look at the universal gravitational constant. It's represented in capital G. So constants are really a mathematical tool. We're going to look at those in the context of gravity. All right, gravity here is defined as an attractive force between two objects due to their mass. So mass exerts itself as an attractive force. Two objects with mass, Einstein viewed it through space-time, that they would kind of cause a little dent in space-time that drew objects towards each other. Newton views it as more as a force. No matter how you look at it, it's um, this attractive nature between two objects. So the sun and the planets are attracted to each other. That maintains orbits. The Earth and the moon attracted to each other maintains an orbit. Your body and the Earth have a gravitational attraction to each other that holds the two objects together. So any two objects with mass have some sort of gravitational attraction to each other. It can be represented as a force. And that's what this right here, this equation is talking about the force of gravity. So looking at Newton's viewpoint, seeing gravity as a force, it can be represented here. I don't really like these notes because it has mass represented with a capital M here. I prefer mass with a lowercase m, but that's okay. Life goes on. Um, it's it's equal to g times m of object 1 times m of object 2 divided by r squared. So what that is, we'll go over that later. I don't want to go into too much into that. There's a whole slide about that later, so I don't need to start drawing a bunch of illegible things here that would be hard to read. So let's take a look at gravity on a planetary scale. You can see Earth, what we know of here, Earth at our 9.8 meters per second squared. That's gravity on Earth. So when you plug Earth's measurements into the gravity equation. Sorry, I really didn't like that arrow. You get 9.8. We can do that later if you guys want to. Maybe I'll do that as like a side video for tomorrow. I'll put that on the to-do list to do a let's calculate Earth video. But when you put it into the equation, you get 9.8. Mars is a smaller planet, less mass. So Mars, you're accelerating at less than half the acceleration of Earth. You'll be hopping around up there on Mars. And the moon is way less. So Mars, they wouldn't be bouncing around as much as what you saw the astronauts on the moon bouncing around. The moon is smaller than Mars even. And then Jupiter, on the other hand, very large object, huge mass. Let's get this arrow to Jupiter. Huge object, very, very large acceleration due to gravity. So you would feel a lot of pressure, very large force normal on your feet. Might even force you down onto all fours to relieve that pressure because you would feel about 3 times as heavy. So whatever you weigh here on Earth, say you weigh 130 pounds, multiply that by about 3. So about 390, a little bit less. Let's call it 380 pounds on Jupiter. And that's for a reasonably small person, even. So that would be feeling a lot of gravitational force on the surface of Jupiter. And again, it's because of the mass. Because Jupiter is a very large object in terms of mass, has a lot of matter. It really pulls towards you with a lot of gravitational attraction. So let's look at a couple of hypothetical questions here. When an object's mass increases, what happens to its potential force of gravity? So a bigger object, a larger planet, larger star, whatever, bigger Death Star, is it going to have more gravity, less gravity? Doesn't matter. And also the second question, when you increase the distance between two objects, what happens to the gravity? So Mercury is very close to the sun. Pluto is very far away from the sun. Do they have the same amount of gravity from the sun because of that distance? Does one have more than the other? How does mass impact gravity? How does distance impact gravity? We haven't really talked about that yet. We talked about it a little bit, especially mass, if you were paying attention. We talked about it a little bit. I'm going to not talk here for, let's say, 45 seconds and go ahead and think it through. So here are the answers to that. So yeah, larger objects, and number one, larger objects, more massive objects, I should say. So not just like volume. A big giant balloon is still not going to have much mass. So larger, more massive objects have more gravity. Closer objects also have more gravitational attraction. So the further two objects are apart, the less gravity they feel from each other. So in that situation we discussed earlier, Mercury would feel more gravity from the sun than Pluto because Mercury is a lot closer. As promised earlier, here's our look at the mathematics behind all of this. Again, I wish those m's were lowercase. I like lowercase m's for mass. That's how it's typically represented. But regardless of the case of the m's, the equation stands that the amount of force between two objects is equal to that. And before we get into it, I want to bring up Newton's third law again. So there's two objects. Let's say one of them is the Earth, one of them is the Moon. Let's say we're talking about how strongly do the Earth and the Moon pull on each other. That force is going to be the same because of Newton's third law. So the Earth pulls on the Moon and the Moon pulls on the Earth with the same amount of force. So it doesn't matter which one is object one, which one is object two. It really doesn't matter at all. You just need to get them both in there because they're going to have the same force, right? When you look at the free body diagram. So let's do that. I have this pen tool here. So here is the Earth, square. Here is the Moon. The Moon also became square. That's weird. They're pulling on each other. So the Moon's pulling on the Earth, causes the tides and all that good stuff. The Earth's pulling on the Moon, keeping it in orbit. Those two forces would be the same amount due to Newton's third law. That is the third law pair. They're pulling on each other with the force of gravity. So before we get too far into this, let's make sure we recognize that when two objects are pulling on each other, they have the same amount of force. So here in the equation, we've got the mass of the two objects. So in this example, we've got the mass of the Moon, the mass of the Earth. I'm sorry, I can't live with that. Let's try a different color for good luck. Mass of one of the objects, mass of another object. That's better. R is the distance between the two objects. Let's make that green, I guess, is what that says. So R is the distance between the two objects. You may ask, why is it R and not D? I've seen it represented as D, but usually it's R. Let's look at that, actually. That gets into something we'll get into a little later on in this unit this week with Coulomb's law, but it's something called the inverse square law. It's this idea that things go out in spheres. This is a three-dimensional universe, and things go out in spheres. So basically, there's the Earth, right? And it's a sphere. Earth is this nice sphere here. Let's see if I can try to add a three-dimensional shape into it. I did a pretty good job. And let's use light green for gravity. Green for gravity, and it's pulling kind of this gravitational field. Got this field of gravitational force pulling everything towards it in kind of a sphere, right? And so what do spheres have? Spheres have the radius. So it's got this radius of gravitational influence here. So that is why they use R, because it's like a radius. These two objects have a radius of distance between each other, and that's why they use R. So physics really happens in spheres. The universe is a very spherical, friendly kind of place. Humans have kind of evolved to like rectangles and squares and grids, but the universe math, it tends to work a little bit easier in spheres and circles, and physics is no exception to that. So we use R for radius. So that's a very common question. Why do we use R and not D? That's why. This radius idea. So anyway, M are the masses of the two objects. You multiply those together. In the denominator there, you divide it by the square of the distance between the two objects. And then we have G. I haven't forgotten G. G right here, the gravitational constant. That's the universal gravitational constant. I just realized a little typo here, but I've already talked so much and drawn such a nice sphere, I'm not going to go back. So let's see if I can keep my good penmanship up with my mouse here. I'm getting better at this. A-N, not the best ever, but it works. Constant, the universal gravitational constant, not force. Sorry about that if that was in the Poggle wrong yesterday. It's a constant. So what that is, it tells you how much mass you need to get some force at a distance. So when you plug these units in here, here's the units for that constant, and you can see it's a very small thing, times 10 to the minus 11. So it's 0.0000000000000000667 newtons meters squared per kilogram squared. So it's extremely small, which again it explains why gravity is so small, right? You're not sucking things to you in your room right now through your extreme gravity. Gravity is a reasonably small force, as shown by that very small 10 to the negative 11th. The units there, I just circled the units and I didn't talk about the units. Now we are going to talk about the units. Newton's meter squared per kilogram squared. It's just mathematical jargon. It basically means if you take that and you multiply it by a couple masses, you'll get rid of the per kilogram squared, which is what happens here. We multiply it by 2 masses in the equation up top there. That's not an arrow, but that's okay. You get the point right here. Up in the equation, we multiply the constant by 2 masses, and that gets rid of this divided by kilograms squared. We multiply by kilograms, we multiply by kilograms again, get rid of a divided by kilograms squared. And same thing here on the bottom, we divide by meters squared, which gets rid of this meter squared and leaves us with newtons. Newtons, which is what we want for force. So all of those units nonsense, that newtons meter squared per kilogram squared, just basically says, hey, here's a number that can turn mass and can turn distance into a force. So if you take 2 masses and a distance between them here, plug it into this wonderful equation we have that I've scribbled all over up here, then we'll get the force of gravity between them. We'll get this right here. So in that case, if we plugged mass of the Earth into here, we plugged mass of the Moon into here, we plugged the distance between the Earth and the Moon into here, and we plugged the constant, that 6.67 times 10 to the minus 11, into there for G, we would get the amount of force between the Earth and the Moon. Which would be reasonably large, right? You'd imagine it takes a reasonably large amount of force to hold the moon in orbit. It's not a small thing. And so maybe we'll do that on the extension tomorrow too. Who knows? Who knows where we're going to go with this in this remote learning times? That's the basic math there of the force of gravity. Let's do a few examples. It's example time. It looks like we've got a rubber ducky and Albert Einstein. That's pretty cool. A couple pretty small things when we're talking about the universe, right? Albert Einstein and a rubber ducky are small. And let's see how small. So we're looking at gravity. So here's our equation. Here's our little diagram representing the distance between the two. And all the information we need is in the problem statement there. I'm not going to read it for you. Basically, how much gravity is between these two things. So let's do the work. We've got our equation here, so I'm not going to waste our time writing it again. Here's our equation. All right. What's the force? Force is equal to G. So G is 6.67 times 10 to the minus 11th. I think I can draw that easily enough. Nice. I know it says it wants units. I apologize. I'm not going to write all that with my mouse. I'm going to maybe invest in a touchscreen here. Let's see when those Trump stimulus checks comes. Maybe I'll get a nice touchscreen or something. Who knows? For now, you do your units on paper. I'm not doing units with a mouse. So there's G. I like parentheses. Mass 1. Let's call rubber ducky object 1. Let's call Albert Einstein over here object 2. So mass of object 1 is 12.4. You gotta be kidding me. That's a massive rubber ducky. The 30-pound rubber ducky. That would even be a big regular duck. Yeah, I think. Whatever. 12.4 kilogram atomic rubber ducky of doom. And object 2 is Albert Einstein, who's a mere 72.5 kilograms. He's barely 5 times larger than his rubber duck. So, for all you out there with your hand-sized rubber ducks, you didn't know what you were missing. So, that's the numerator. We've got our gravitational constant G, a very small number. It looks big. but in reality it's very small because that's a negative 11, 10 to the negative 11. Very small number. Really big rubber duck there, 12.4 kilograms, and Albert Einstein weighing in at 72.5 kilograms. Got to divide by the distance between them, which is 3.5 meters. So everything's already in kilograms, meters, and seconds. That's going to be very important going forward here. Remember all those units that we were talking about for that gravitational constant? Those all depend on kilograms, meters, and seconds. Newtons are made of kilograms, meters, and seconds. So all these equations, all these numbers we use from here on out, they depend on kilograms, meters, and seconds. If you don't have those, you better change your units until you get those. That's the only way you can use these equations, really. Are there other constants that work? Sure. When you get to chemistry, maybe not high school chemistry, but certainly college level advanced chemistry, you'll use many variations of the same number, it's called R, with different units. But we're not there yet, so keep it easy on yourself. Don't worry about chemistry or any of that nonsense. You want kilograms, I'll put it over here. Kilograms for mass. We want meters for distance. We want seconds for time. That's not even an S. Let's try that. Whatever. Good enough. That's what we want. Everything will be dandy if you get those units. So plugging this all into a calculator, that sounds annoying, but you know what? We're going to do it for the sake of notes. So I'm going to plug this into my calculator. Maybe you've already done this already while I was rambling. You probably have. You guys are way ahead of me. Can't enter more than 10 digits. Okay, fine. I'll do it. Scientific notation. Be that way. 6.67 11. Why is it? Oh, that's natural logarithm. Wow. Okay, my calculator is being very annoying. So let's just go to Google. Let's use handy dandy Google. I like Google more than a regular calculator anyway. So I'm switching over to Google. I apologize for the delay. 6.67 times 10 to the negative 11 close parentheses times 12.4 times 72.5 divided by 3.5 squared, close parentheses. Seems reasonable. Yeah, I like it. If you got something different, you may be right. I'm not going to guarantee this is right, but it's definitely seems reasonable because it's a very small number, and I expect it to be small because Rubber Ducky and Albert Einstein aren't gravitationally pulling each other really at all. I got about 4.89 times 10 to the minus 11. Wait, minus 11, not minus 11, sorry, minus 9. 10 to the negative 9th newtons. And I apologize for the long delay there. I didn't expect my calculator to wimp out on me so bad. But it gave you some time to calculate it yourself. It was as simple as that. You took the numbers, you put them in the equation, boom, you know gravity. And as it turns out, gravity is pretty worthless when it comes to two objects sitting on the planet Earth. Any gravity between two objects on the planet Earth gets overwhelmed by the planet's gravity because Earth is so much larger than anything on Earth. So very, very tiny force there between those two objects. So next up is a practice where we actually do something useful. We look at a problem where it's not just, two tiny little things. We're going to look at a couple planets now. Okay, like I said, a couple planets. Unfortunately, they're very far apart. You can see this is a positive 11 here. Give me my pen. Yeah, positive 11, which is unfortunate. That means they're very far apart. However, they're both very big, right? These are two planets. They're actually very similar in size. The So those pictures, those drawings aren't really close. Venus is very close to the same size as Earth. It's often called Earth's twin or evil twin because anything that goes there dies instantly. But other than that, it's pretty much the same. So let's look at how attracted to each other these two planets are. They're big because they're planets, but also far apart because they're, well, planets. Let's look at gravity. Again, we've got our universal gravitational force equation right there, bottom right. Plug in the numbers. So F equals, again, 6.67 times 10 times minus 11. And the units there are newtons times meter squared divided by kilogram squared. I'm not going to write all that with my mouse. I've already wasted enough of your time. But make sure you know the units. Basically, it makes it so everything cancels out nicely to newtons. When you have a force, you should have newtons always. Doesn't matter what kind of force we're talking about here. When you have a force, you want to end up with newtons. So if everything cancels out hunky-dory and you end up with newtons, good job, you probably did it right. That's a good way to check. So our mass of object 1, oof, I have a lot to write here. Let's call Earth object 1 because we're biased, because we live there. Oh, Earth. Earth is planet number 1. .97 times 10 to the 24 kilograms. I'm not going to bother writing units. Ugh, I'm getting a little sloppy here. Sorry about that. And let's look at 4.89 times 10 to the 24. Oh, my hand's starting to hurt. Okay. I feel better. So there's our numerator. Lots of numbers up there. This is going to be an annoying one to punch into Google. I'm at least getting a clean dividing line here for our fraction. Clean enough. Okay. And divide by the distance squared. So that's not parentheses. That's not an eraser. Okay. 3.8 times 10 to the 11. So hopefully that scientific notation portion of the POGL made sense to you here, because we're using it a lot, as you can see. It's something that's very helpful for large objects. Let's clean up that parentheses there. That's actually a solid parentheses. So basically, it replaces having a lot of zeros at the end of the number or before a decimal. If you haven't used it before, a lot of math classes already taught it, and it was also in the POGL from yesterday. So if you understand it, awesome. Don't wanna repeat it and use up your time. But if you don't understand what these times 10 to these numbers mean, please let me know. Send me a message. We'll work through some of that stuff on the POGL together. Make sure you understand it. We're going to be using it a lot, and I'm just going to roll with it as if you know it based on your math class knowledge and the POGL. So if it's not making sense to you, if this stuff here, this stuff here isn't making sense to you, the times 10 to all these numbers, let me know right away, because that's going to be important going forward. I want to check in with you, video, chat, whatever we can do to make sure that we clear up anything on that. So, plugging all of these numbers in is the last thing we need to do, and then you're free from today's science. So, going to Google, 6.67 times 10 to the negative 11th times 5.97 times 10 to 24th times 4.89 times 10 to the 24th divided by 3.8 times 10 to the 11th in parentheses, and then all of that squared. You got to be careful with your parentheses here on your calculator. There's this website, Wolfram Alpha. That's high. That's a lot of force. Hang on. Let me just assess this in my head here. So 10 to the minus 33, 34, 20. Okay, never mind. That does seem reasonable. Okay, these things are tugging on each other pretty good. Actually, it's not all that much considering how large these objects are. That actually makes sense. So a reasonable amount of force. But remember, these are very big objects, so Newton's second law, F equals ma. They're not going to have a huge impact, even though it's a pretty big force. So 1.35 times 10 to the positive 16. It's a huge force. That's basically a 1 with 16 zeros after it, newtons. But we're not being pulled towards Venus that much. And again, it's because the Earth is so large. So the Earth and Venus both are up here with this 10 to the 24th kilograms. And the force between us is only 10 to the 16th newtons. That means there's what we call 8 orders of magnitude. So basically, the acceleration of Earth towards Venus is 0.0 with 8 zeros, 1 essentially towards each other. So a lot of force, not much acceleration, because we're talking very, very big objects. Planets, right? Planets are big. So that's what we've got going on here on a planetary scale. Again, calculating force of gravity is pretty simple. We are dealing with big numbers and small numbers with a lot of zeros involved. That's where the scientific notation comes in. But in the end, it's just this equation right here. The force between two objects because of gravity is equal to the gravitational constant times the mass of object 1 times the mass of object 2, and you divide all of that by the square of the distance between the two objects. And you want everything to be in meters and kilograms, and everything will work out great. That's it. Make sure you fill out the exit ticket to get today's points. I'm really liking those exit tickets. They're helping me if you guys have questions. I might make a frequently asked questions document again for this. If there's a lot of good questions, we'll see how it goes. But yeah, get those exit tickets turned in and have a good day.